All right, this next example, example 3, we have a trapezoidal irrigation gate. So if there's an irrigation channel and then we want to close it so the flow stops, we could lower this trapezoidal cap or gate down so the flow of the water, which we can imagine is either into the page or out of the page, that gets cut off by that. So the fluid, or the surface of the fluid, the surface of the water, would actually be exactly the same height as this gate here. So I'm going to go ahead and say there's the surface of the water, and I'm going to go ahead and say that the surface of the water coincides with y equals 0. Okay. So what we can do in this case is, this one, the geometry is a little bit more complicated. So it takes a little bit more finagling than the previous example to get what we want. But the same procedure does apply. The procedure always is as follows. Draw a thin horizontal rectangle at some arbitrary y value, y. So this right here is some y value, y. Now, unlike the previous example, where I directed my positive y-axis downward, I'm going to go ahead and be more traditional and put my positive y-axis upward, just so you can see how things change slightly. It's really not much of a change. You just get this negative sign floating around. So here is our thin horizontal strip at a arbitrary y value of y. What we need to know here is really the width of this, or the length of this line segment. Here, the thickness of my line segment is dy, so I'll go ahead and write that in. Okay, so to figure out the width here is going to depend on, really, it's going to depend on these two lines. Okay. So I'm going to draw these guidelines. So I'm going to draw these black dotted lines vertically, where so sort of splitting a triangle up into a rectangle in the middle with two triangular end caps. Now, I'm not a perfect artist, but let's assume that these two triangles here are equal. They're the same. So that means if the larger base of the trapezoid is 5, the smaller base is 3, that means the difference is 2 meters, and if these two triangles are equal in size, then they must be 1 meter apiece. So this little piece right here is 1 meter, this little piece right here is 1 meter. Okay. So what I can do is choose where to place I can choose where I would like to place the origin. So what I'm going to do here is I'm going to place my origin right here. So there's my positive y-axis. And then here we have our x-axis. Positive x-axis to the right. So our standard coordinate system, and I'm choosing to place the origin right here where they intersect. That didn't have to be there. It could have been elsewhere. It will change slightly what your expressions look like, but the overall procedure should be the same. So if this is 2 meters, or excuse me, let's say this is y, so that means I can focus on this triangle here. Well, these two triangles, really. Small triangle and big triangle. These two triangles are similar triangles. So let's label some of these lengths. We already took care of this being 1 meter. And we already know that this distance right here, from here to here, that's some y value, y. Okay? So then, if this full distance is 2 meters, and this portion is y, then this distance here would have to be, well, take this y value, subtract this y value. the y value down here is y equals -2. So this distance here would be y minus -2. So y plus 2 would be this distance. And this might look a little strange to you, because if this distance is y and then we add 2 more, wouldn't that like put us down here? On one hand, yes, but technically no. This distance here, if I took whatever this distance is, so some positive number, and I added it to this distance here, then I would end up somewhere down here. But the thing is, because the positive y-axis is directed upward, that means whatever y value I'm associating with this displacement from the x-axis, this is actually a negative y value. So if I take some negative value and I add it to 2, it's actually going to be something less than this full distance. It actually is this distance here. So remember that whenever you're calculating distances, vertically at least, you can do top y value minus bottom y value, and that will always work. Same thing goes for horizontal distance. You just do the x value on the right minus the x value on the left, and that will tell you that horizontal distance. Okay, so we've got this length, y plus 2. We've got the full length, which is 2. And what would this distance be? Well, that distance would be x. Because this is the y-axis, so if I am measuring something that's attached to the y-axis, that by definition is x. So we have similar triangles. So the big triangle has a height of 2. It has a base of 1. The small triangle has a height of y plus 2 and a base of x. So the relationship between these two triangles, they're proportional. So I can do this length divided by this length, and that will be the same ratio as this length x divided by this length y plus 2. And we're going to need that for this next part. We needed a relationship between x and y because ultimately we want to know the length of this line segment. So pressure is depth times the density of the fluid rho times the acceleration due to gravity, which is g. So the depth is the distance below the surface of the water. So you might be tempted to say that the depth is y, but the depth is not y. This differs from the previous example where it did equal y. And the reason why it was equal to y is because we chose to direct the positive direction of the y-axis to be downward, which is slightly counterintuitive, but in that case it makes it match up nicely. But again, there's a difference between the y value and the distance between two things. So this y value, all the y values on this horizontal line are pretending are just y, but this distance is actually going to be top y value minus bottom y value. So the y value of the top line is y equals 0, and the y value on this bottom horizontal line is just y. So top y value minus bottom y value, the depth is actually negative y. Again, that seems weird, but since we are below the x-axis, the actual y values themselves are negative numbers, and depth is a positive number. So this negative takes care of the inherent negative in the y value. So we get a double negative, which gives us a positive value. So the depth is y, the density is rho, and the acceleration due to gravity is g. So the pressure is negative y rho g. The area, in this case, is just going to be the width times the height, but in all these fluid force problems, it's going to be dy every single time. So we really need to figure out the width, and that's usually the hardest part in any problem, is figuring out that width. So the width here, we know that this is x and this is x. So we have x plus this middle portion, which is 3 meters. So it's 3 plus x. So 3 plus 2x. And here is exactly why we need similar triangles, because we need everything in terms of y before we integrate. So we have to somehow exchange this x for a y. The similar triangles provides a way to relate x and y. So I will multiply this expression, I'll cross multiply. So we'll have 2x equals y plus 2. So 2x is y plus 2. So the area is 5 plus y dy. So the fluid force will be the integral of our pressure times our area. So this quantity times this quantity. I'll pull out the constants, so the rho and the g will come out front, and we'll be left over with, also I can pull out the negative 2, TOO, not the number 2, I can pull it out also. So then we're left over with y times 5 plus y dy. And then we have to integrate over the range of y values that correspond to the surface of the plate. So the top of the plate is y equals 0. The bottom of the plate technically is y equals negative 2. So we would integrate from negative 2 to 0. And there we have it. This would give us the fluid force over the plate.